Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for these students. I pray that you'd just be glorified in what we do this morning. I just thank you for the hard work of the students. I pray that it would be edifying to them, that they would have learned math through this process, and that we would encourage them to just keep up the good work. Lord, in your name I pray. Amen. All right, so a stack of homework. Thank you, thank you. All right, so today I'm going to continue our discussion of how to integrate trig functions. And thanks. I will start with a discussion of integrals of secant. I think we did integral of secant theta last time, right? We did a weird u substitution. It was like u equals secant plus tangent. Let's see here. Let me just remind you of a couple of easier things. Well, first of all, of course, it's weird, but integrals of like even powers of secant are easier. So if I look at secant to the fourth theta, d theta, I can do this as secant squared theta times secant squared theta d theta, right? But tangent squared plus 1 is what? It's secant squared theta. So you see what this is the integral of 1 plus tangent squared theta, parentheses. And then the secant squared theta d theta, well, that's precisely the differential of the tangent. So that's d of tangent theta. So you can see we can make a tangent theta substitution, and we get tangent of theta plus 1/3 tangent cubed theta plus a constant. Okay, so integral of, thanks sir, integral of a even, thank you, integral of an even power of secant. You can kind of see that if you can do this one, well, remember what's the integral of secant squared? Tan. So that you know, these aren't bad. Odd powers, on the other hand, are kind of a drag. I mean, I encouraged you last time we should just memorize this formula, basically. Integral of secant theta d theta is the natural log of the absolute value of secant theta plus tangent theta plus a constant. And that's, we derived that last class. It's worth memorizing. Okay, so that said, we can go on and we can try to integrate the next hard case for secant, which would be secant cubed. All right? Secant cubed theta, how are we going to integrate that? Well, I'm going to be lazy. Oops, that's not helpful. Woo. So, integral of secant cubed theta. Sorry, now you have a green dot burned in your retina, but oh well. Just don't stare at it too long. It's like looking at the sun or something. So integral of secant cubed theta. Oh man, I think this might be a little bit of overkill. I told my former student who went to China, she's like, could I get you anything? I'm like, a laser would be nice. So this is what I got. So that's pretty cool. So secant cubed theta is actually kind of difficult. Almost any integral that I can think of. When I was teaching Calc 2 at NC State, I'd be walking back to my car with my wife, and I would just say, how would you integrate blah? And she'd be like, And then she'd tell me the answer. I'm like, okay. But then, secant cubed. Secant cubed took her about half the walk home. Like, this is not an easy one. It is harder. Yeah, like a full 10 minutes of walking. Yeah.
Got a little confused on that first thing you did where you had 1 plus tangent squared theta d theta. Where did you get d tangent theta?
The derivative of tangent is secant squared. I mean, what's going on here is I'm making a u equals tangent theta substitution without writing u. It's the sneaky implicit u substitution notation. that I roll out from time to time as to confuse the students. All right, so I did my job? Okay, good. And as to delight those who like to write less. So at least one person's unhappy with everything I write. So much is sure. Okay, getting back to the unhappiness. Here, secant squared is tangent squared theta plus 1, right? But then I can do what? I can distribute. See this 1? Whoa. I can see a green circle. So the secant theta is from the 1. And so the integral of secant, I'll stop using this thing. The integral of secant theta is natural log of secant plus tangent, right, by yesterday. And then this other piece over here, tangent squared secant theta d theta, doesn't look much better than what we started with, but in fact it is, because if we do integration by parts on that, what happens, right, is that we get back where we started. See, if I let u equal tangent theta and dv secant theta d theta, well, du is secant squared theta d theta, right? And if v is secant tangent, then v is secant, because the integral of secant tangent is secant. All right? So then we do what? We do uv minus the integral of v du, and what happens is we end up with these two terms, but then this is again secant cubed. So I've come back where I started, but with a minus. In other words, I can solve for the integral by adding I to both sides, right? And that gives me 2i is equal to the natural log of secant plus tangent plus secant tangent. Divide by 2, there's the answer. Integral of secant cubed is 1/2 the natural log of the absolute value of secant plus tangent plus secant tangent plus a constant. I do not expect you to memorize this. However, I think if I was to challenge you on the test to do something like integral of cosecant cubed theta, you might have a shot at it now. I still think it's a difficult problem. Any questions about the integral of secant cubed? Is there a reduction formula for secant? Probably. I don't know those things. I mean, I don't have them memorized. For some reason, I don't like reduction formulas. I don't know what's wrong with me. I can't stomach them. I mean, I'd rather learn how to integrate sine order by order than remember some grand glorious reduction formula. I suppose the reduction formula is more logically efficient. But you still have to bootstrap your way up to wherever you are at each order. I don't know. It's a lot of people like them. Probably a good reason for that. I'm just not such a person. Maybe Dr. Skimbordas likes them more. Maybe you should go to his class if you want those. I don't know. I'm not sure. He probably doesn't care. I don't know. There are, of course, reduction formulas for most of these things. That's true. Yep.
Like, the thing that I don't understand with this problem, I'm sorry, is did you take the integral of 1 squared theta?
Are you talking about the one on the board?
Yeah.
This is the integral of 1 plus u squared du if I set u equal to tangent theta. That's all.
Okay, thanks.
Mm-hmm. The point of what's written there already is that if you understand it, you don't even need to write the u. I don't deny it's a higher level of thinking. It's like the next step in sophistication of u substitution. But whatever. Certainly you don't need to understand that notation in order to make an A in this course. I'm just telling you it is a labor-saving notation that's worth seeing. Yeah. Yes? Oh, no. I did that yesterday. Oh man, I forgot to. I was going to berate the earlier class for not telling me I didn't distribute the half in my earlier example yesterday. Thank you. That was a very helpful comment. I think I didn't distribute that half earlier today as well. Oh man. Well, I'm going to have to give them a talking to. I tell you. All right, let's move on. Any other questions about this? Yep.
Why is it QI?
Because I've got minus I on this side, and I've got I here. So if I add I to both sides, I'm just left with this thing, which I could call Pac-Man. So, like, it's the same thing we did with the cosine squared integral yesterday. All right. So at this point, I want to tell you there's one last remaining story I need to tell you about integrals of trig functions, and it's kind of a different thing. It's not entirely linked to what we've been doing so far today. It's kind of a different animal altogether. So let me just tell you a motivating example, a humbling example. This one, sine of theta times the cosine of, say, 6 theta, d theta, equals what? How do you integrate such a thing? Yes, sir? Split up the cosine. That's probably how you'd have to do it with what you guys know. That's not a bad suggestion. You could do like cosine of 3 theta plus 3 theta. That would give you like cosine, cosine, sine, sine. And then those would be of 3 thetas. Then you could break it up into like theta plus 2 theta. That would break it up further. Then you could take those 2 thetas and write it as theta plus theta, break it up further. And eventually you'd be left with things that are like sine theta and sine theta and cosine theta. Yeah. We're not going to do that. Thankfully, the imaginary exponential comes and saves the day. So let's talk about the imaginary exponential again. This is closely tied to the study of phasors. So anybody who's an electrical engineer in here should pay attention to this, because this mathematics is important to the solution of AC circuit problems. Anyway, e to the I theta is equal to cosine theta plus I sine theta. All right, we could take that basically as basic. I would explain to you why this is true perhaps later in this course, or certainly in a different course. But for here, mostly we're just taking this on faith as a good starting point. So if I have I theta, I get that. If I have I beta, I get that. I can solve these for sine and cosine, right? Like either by addition or subtraction. So like addition, I can derive cosine of theta is 1/2 e to the I theta plus e to the minus I theta. If I subtract and do a little algebra, I can derive sine theta is 1/2i e to the I theta minus e to the minus I theta. Okay, so these are sort of your basic building blocks, if you will, for the imaginary exponential technique. These things we need to just sort of have memorized. All right. Once you know these things, though, you can use them and you can do things. For example, I could look at something like this. E to the I theta times e to the I beta should be equal to what? Yeah. If there's any justice, if this notation is worth using, how should exponentials behave? Add the exponents, right? So it should be e to the I theta plus I beta. I could factor the I out. I should have e to the I theta plus beta. I mean, if these are worth using at all, that certainly should be true. In fact, it is. But what is the content of this equation? What does this say? Well, e to the I theta is cosine theta plus I sine theta. E to the I beta is cosine beta plus I sine beta, right? And then on the right-hand side, I have cosine of theta plus beta plus I times the sine of theta plus beta. All right. Expanding. So these two things are called Euler's formula for what it's worth. So I just use Euler's identity if you like. Now, I can multiply these things out. Yes, sir?
What do you mean by the whole like adding and subtracting that you did in the box there? Like,
I mean, you can solve those by adding the equations. Well, I'm sorry, you're right. Before I usually write, fine, just erase it. Before I showed you that if we look at e to the I theta and e to the minus I theta, then we add them, we get cosine theta. If we subtract them, we get sine theta. We talked about that like last time we talked about these. So you're right, I should just erase that and just say these, we derived these previously. There we go. Yeah. Good question. Let's see here. So cosine theta, multiply this out, right? Cosine theta, cosine beta. I squared is what? I squared is minus 1. So I get minus sine theta, sine beta. And so that's equal to, let's see here, cosine theta plus beta. All right. And then, let's see here, plus I times what? On the left-hand side, what do I have? I mean, the right-hand side is easy. It's sine of theta plus beta. There's nothing to do there. Now over here, let's see, what are the terms with I? Cosine theta times sine beta. And what's the other term? Sine theta times cosine beta. Sine theta, sine beta. What do you mean?
where do you get that?
From the product of the sines? I squared is minus 1. Now, if you look at this, so the beautiful thing about one of the really nice things about working with complex numbers is it's just such an efficient notation. Every complex equation has hidden inside it two real equations, right? So if the complex equation is true, it must be the case that separately the real part of both sides match and the imaginary side of both parts match. So the real components matching gives me that this is equal to that, right? See what that is? The adding angles formula for cosine. Right? And if you look at the imaginary, so that says, of course, cosine theta plus beta is equal to cosine theta, cosine beta, minus sine theta, sine beta. And then the other terms matching, right? This one and that one gives me what? Sine theta plus beta. Now, of course, I told you about these the other day, right? But I think maybe you can appreciate what's going on here is I didn't pull them from the thin air. I derived them as a necessary consequence of the laws of exponents for imaginary exponentials. In other words, if you can remember that e to the I theta times e to the I beta is e to the I theta plus beta, and you understand this technique, you cannot forget the adding angles formulas for sine and cosine. They're in there. Okay, now I guess I should confess this has little to do with solving that, but I'm just trying to get us back in the swing of things. And if I do all of this stuff about imaginary exponentials on one day, it overwhelms you. So I try to chop it up into two pieces. All right, so let's get to the order. So what we want to do is find an identity for sine theta times the cosine of 6 theta, right? We'd like to break that up into simpler things. But, you know, why not just do it in general? So what we're going to look at is the sine of theta times the cosine of beta and see if we can't derive an identity for that. All right? So what is this? Sine of theta is 1/2 e to the I theta minus e to the minus I theta. And cosine beta is 1/2 e to the I beta plus e to the minus I beta. All I did was use what's in the box to start with, right? For theta and then for beta. The reason I've done that is because now I can work out the trig identity using laws of algebra. Yes, sir?
On sine theta, wouldn't there be if
Oh.
1/2I?
Thank you. Very good. Yeah, definitely we need that I there. That's important. So let's see here. This gives me 1/4I, right? Times what? Let's see here. So first of all, if I do e to the I, so you're just basically expanding here, e to the I theta times e to the I beta gives me e to the I theta plus beta, right? Then, if you look at these two multiplied, we get minus e to the minus I times theta plus beta. I factored out the minus, right? So first with the first, last with the last. Now I got to look at the product of red and blue and red, right? So like the other terms there would be what? So like this one with that one will give me plus e to the I theta minus beta. And then finally, the one I haven't done yet, I'll do in black. This one, this with that, gives me minus e to the minus I theta minus beta. Now the reason I've written it that way is I'm looking ahead to what I'm going to do. I'm trying to regroup these things as signs. So I want it to look like this format. And I've achieved that, you see. One more step here. So this is 1/2, 1/2I, e to the I theta plus beta, minus e to the minus I theta plus beta, and then plus 1/2, 1/2I, e to the I theta minus beta, minus e to the minus I theta minus beta. Now, if you look at this, you can see what's going on. What's this first term here? Sine of what? Sine of theta plus beta, right? And then what's the other one here? Right, plus 1/2 sine of theta minus beta. So therefore, we have the following identity. Sine theta cosine beta is in fact 1/2 of the sine of theta plus beta. Well, I'll just distribute the half plus 1/2. I mean, you can factor the half out or put the 2 on the other side. It's all up to you what you think is the best way to remember this thing. I don't know. I personally don't. I usually forget this thing. I have to rederive it when I need it. Unfortunately, it's one of those things for me. There you go. Something we didn't know, right? Now, you could derive this by doing what? If you took sine of theta plus beta and sine of theta minus beta, and you feed that to the adding angles formulas, and you add them, it'll simplify back to this. But that begs the question, why were you looking at sine of theta plus beta and sine of theta minus beta to start with? In contrast, this imaginary exponential technique, we just started with what we want. We do algebra, and out pops the identity that we're looking for. So now, you see how we do it. The integral, excuse me, of sine theta times the cosine of 6 theta is what? It's 1/2 times the integral of what? Sine of 7 theta, right? Plus the sine of what? Yeah, minus, what, you say minus 5 theta? Yeah. Of course, sine is odd, so we can pull the minus out. And just long story short, we get 1/14 minus 1/14 cosine of 7 theta plus 1/5 cosine of 5 theta plus a constant. And there you go. That's how you integrate that. Honestly, the integrals here are of secondary importance to the trigonometry I'm showing you. Because really, as scientists and so forth, whatever your major is, it's something technical if you're taking this class. It's really important to be able to manipulate sine and cosine as many different ways as we can. Because sine and cosine model things that have sort of a wave nature, right? So being able to add to sine and cosine like this is the ability to be able to, say, understand how waves superpose, interference, and all kinds of things. It's important math. Yeah.
Why was the 1/5 not
Yeah, that's a very good question. Of course, that mistake I made on purpose for your learning, as usual. Thank you. Good question. I wonder if I made that mistake earlier today, and if they caught it. If you don't mind, I will be lazy now and recycle my earlier lecture. Obviously, yes, sir.
So when we think of sine theta times cosine 6 theta, we think about that in ways of sine theta and cosine theta. That's what you think about it?
I'm thinking that theta's theta and that beta, why did I do that? I'm thinking beta, I think it reflected back to me that time, 6 theta. So I'm just making a substitution into the identity we just derived. Yeah. Yeah. I need to get some kind of attenuator for this. I don't know. All right, there, that's safe. All right. So this over here, sine theta, sine beta, and cosine theta, cosine beta, these, we'd also like to know identities for these, right? My point to you is once you know this one, if you know calculus, you can get the other two pretty much for free. Yes, sir?
Where exactly did the 7 and 5 come from?
6 plus 1 is 7. 1 minus 6 is minus 5. Theta plus beta, theta minus beta. Yeah. Now over here, so to understand, to get sine, if I differentiate the identity we already have with respect to, yes, sir?
Sorry, just to go back, where did the negative go? Where did the negative go?
Well, differentiate, if you, it's in here somewhere. No, if you differentiate this, we get back a minus, right? So, I mean, this minus pulls out because sine is odd. No, I mean, I could do this, if that's helpful, but I don't need to. I mean, that, if we differentiate cosine, we get minus sine, and then the 5 pulls out from the chain rule, and then 5 over 10 is a half, which is what we have in the step before. And there should be a sign difference, like a SIGN difference between this term and that term, as there is down here. So at least it's consistent. All right, any other questions before I go on? That's good. You guys should keep asking questions. So here we have, if we take this identity and I differentiate it with respect to beta, holding theta fixed, right? That changes this cosine to a minus sign, and it changes both of these sines to cosines. The chain rule is boring for this one. The chain rule is interesting for this one. It pulls out a -1. So see what I did? Differentiate both sides. You get minus sine theta sine beta, cosine theta plus beta, minus cosine theta minus beta by the chain rule. And then multiply by the minus, and bam, here's the identity for sine sine. It's 1/2 cosine theta minus beta, minus 1/2 cosine theta plus beta. In fact, once you know any one of these three, you could differentiate to get the other two, I think. If I, on the other hand, differentiate that identity with respect to theta, sine changes to cosine this time. I get cosine cosine. And on the flip side, I don't get any minuses because the chain rule is boring. The derivative of theta plus beta with respect to theta is 1. The derivative of theta minus beta with respect to theta is 1. So the chain rule doesn't do anything interesting on the second differentiation, because there's a difference between theta and beta, how they appear in the formula over there. But there you go. There's your trig identities for these sorts of products. Yes, sir.
How come when you take the derivative of sine theta minus sine beta, so you get minus sine theta sine beta?
Because here I'm differentiating with respect to beta, holding theta fixed, so the derivative of cosine is minus sine. In contrast, down here I'm differentiating with respect to theta, so the cosine beta is a constant, and the sine theta differentiates to cosine theta. So it's the difference of sine and cosine. Oh. Where did there's the juice. Well, folks, that's about all I have for integrals of trig functions, give or take. Now, tomorrow you can ask me some questions about them if you got them. But we're really moving on to the next section, which is known as trigonometric substitution. Trig substitution should not be confused with integrals of trig functions. Integrals of trig functions is something we need in order to complete the task of trigonometric substitution, but trigonometric substitution is a different animal. Now, trigonometric substitution is a big topic. It's going to take me more than the remaining time today to do. What I'm going to do today is just try to show you 2 or 3 examples that illustrate the method. Next class, at the start of class, once we're done with the homework questions, I'll try to give you a grand, glorious summary of the method. All right? That's where we're going. So, but before I do that, I'll just kind of give you a preliminary goal. Is something like remove radicals is a somewhat decent description of what the goal is. That's the idea. So here's a fundamental example. It's a good place to start. Integral of the square root of 1 minus x squared. So it turns out that what we do is we let x equal to sine theta. Now, before I go any further, I just want to point out the weirdness of that. A typical thing is something like the integral of, I don't know, say sine of x squared times 2x dx, right? And so to do something like this, we do what? We say u equals x squared, right? du is 2x dx, something like that. So this is integral of what? Sine of u du, blah, 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 blah. My point to you, though, is simply this, is that the new thing, right, the substituted variable, the thing we've invented, we've created in order to aid with the calculation of the integral, is the u, right, u substitution. This is the new. This is the old, right? In contrast with this trig substitution, from the very start, something weird's going on. This is the old. This is the new. So the theta plays the role u did before. Really, this is an implicit substitution. Implicit in the sense that I'm not telling you theta equals blah. I'm telling you how theta is wrapped up in the sine function as to describe x. It's an implicit description of the substitution. In contrast, u substitution is explicit. Explicit. Implicit. All right. So once we have that, though, I'll show you why we care. What's 1 minus x squared? 1 minus sine squared theta, which is what? Cosine squared theta, right? And what about dx? Well, dx is cosine theta d theta, right? So we got, okay, there's our thought bubble for what I'm about to do over here, which is that this is actually the integral of the square root of cosine squared theta times cosine theta d theta. Yes, sir?
There should be a dx in the original integral, right?
Oh, most certainly. Yeah, take off all my points. Like, seriously, if you don't write it, I'll take off points. I know. My brother says that I'm just being a jerk when I do that, but I actually think details matter. We kind of disagree about details mattering. I think details matter. They matter less as you go on, but at this point, they matter. Okay. I mean, there are world-class mathematicians who can't do arithmetic worth anything. That can happen. It's possible. But for the rest of us, we should care about arithmetic, right? Okay, so, and dx in this case, it matters. So part of the reason it matters is it's so important, just like with u substitution, you have to change both the integration, both the integrand and the measure, if you will, the dx. They both have to be changed into the new variable, right? So, okay, so we got what, cosine squared theta d theta. Now, how did I know that the square root of cosine squared should just be cosine again? Well, I'm integrating square root, right? Square root is non-negative, so I should keep the plus, basically. And the cosine I have in mind here is based on an acute triangle, so cosine's positive, all right? Hey, but this we know. This is the integral of 1/2 1 plus cosine 2 theta d theta, which we did yesterday, which is what? Theta over 2 plus 1/4 sine 2 theta plus a constant, right? Now, our answer should not be in theta. It should be in terms of what? X, right? So this is 1/2 inverse sine of x plus 1/4 of sine of twice the inverse sine of x plus a constant. So this is an okay answer, but it's not a good answer. It's okay. It's not ideal. I'd give most credit. I'd give almost full credit for this, depending on close to full credit. Not quite, though. It's not quite the best answer. What's the best answer here? The best answer here appreciates the role, the interplay between the inverse sine function and the algebraic functions connected to it. Let's draw a picture. So let's see here. Here's a triangle, right? The triangle, I'm going to put theta. And we've got x sine theta is equal to what? Sine theta is equal to x over 1, right? So the opposite side is x. The hypotenuse is 1. The thing we're trying to remove, the thing we're trying to unravel, the square root, is the remaining thing. See this? That's this, adjacent side. So sine theta is x. What's cosine theta? Yeah, the square root of 1 minus x squared over 1. So I guess we could just write x and 1 here, right? I mean, division by 1 we can omit. But what is 1/4? 1/4 of sine 2 theta is what? Right? Sine 2 theta is 2 sine theta cosine theta. Remember that? And then I can write this in terms of algebraic functions as what? This is actually what? 1/2 x times the square root of 1 minus x squared. And there you have it. That's about the best I can do for this answer. The inverse sine is what it is. See, that's coming from a naked theta. It's a theta just sitting out there by its lonesome. There's nothing I can really do to make that better, as far as I know anyway. And then I've got x times the square root of 1 minus. Now, that's an algebraic function. We much prefer to put our answer as an algebraic function when we can manage it. Okay. So that's a good answer. Yes, sir. Oh, well, if sine theta is equal to x, right? That tells me that theta is equal to inverse sine of x.
That's where it came from when we switched it from theta over 2 to 1/2 inverse sine.
Mm-hmm. Yes, sir. Yeah.
Are there any ways in which like the domain and range should be affected and we can't do it because it would limit the original function for input?
Well, let's see here. I guess the main issue I might worry about is if the domain of integration had negative x. And if I'm thinking of x as being a length of a triangle, I might miss a sign there somewhere eventually. But I usually just think in terms of x being positive, and then if I came to a problem where I had to worry about those issues, I would think more deeply. But I've got enough else worrying about here to not dwell on that at the moment. Let's worry about that trouble when it comes to us. You see what I'm saying? I mean, the domain of this is what? It's between -1 and 1, right? So certainly for x positive, the triangles I'm writing make sense. I guess the question is, what if x was between 0 and -1? Would these things I wrote still make sense? I think so. I'll think more about your question, see if I have something to say about it, but I don't have anything much to add at the moment. Okay, so what if we bump this up a bit? What if we tried to do the integral of the square root of, instead of, let's trade that 1 for an r squared minus x squared dx. Kind of the same thing, but I changed the 1 to an r. Now what? How will I do this one? Factor out an r? Well, you could go that way, but I'm not going to go that way. What I'm going to do is I'm going to let x equal to r sine theta. And so doing that, I get x squared, I get r squared minus x squared is equal to r squared minus r squared sine squared theta. Of course, I can factor out the r squared, and I get what? I get r squared cosine squared theta. And I get dx, of course, is r cosine theta d theta. So with this little trig substitution thought bubble, I get the following. The square root of r squared cosine squared theta times r cosine theta d theta. I'm assuming, of course, r is positive, all right? So I can pull out an r squared integral of cosine squared theta d theta is what I'm left with again. But it's different this time, right? The substitution is not quite the same. I mean, the cosine squared integral is the same. So we're, again, going to get r squared times theta over 2. How did it go? Theta over 2 plus 1/4 sine 2 theta. And I want to simplify that, so I'm going to rewrite that in terms of sine and cosine. So that's 1/2 sine theta cosine theta there. Now I'm in good position to write the answer as nicely as I can. So then what? Yeah, the triangle, but this is a slightly different triangle, right? This time we have sine theta is what? X over r, right? So I've got my theta here, my opposite is x, my hypotenuse is r. The thing I'm trying to remove, the radical, is here, square root of r squared minus x squared, right? So what does that make cosine theta? Right, from the triangle. So what's my answer? R squared times 1/2 inverse sine of what? This time, x over r. And then plus what? Plus 1/2 sine theta cosine theta. So that's x over r. So it's basically going to be x times the square root of r squared minus x squared divided by, 2r squared if you want to write it that way. There we go. Or I suppose I could multiply this out. This would be r squared over 2 inverse sine of x over r. The r squareds cancel, right? So I'm left with plus 1/2 x times the square root of r squared minus x squared. I forgot my constant, sorry. Plus constant. And there you have it. When does class start? Oh, man. Well, one more thing, and then we'll be done for today. An application of this that's pretty neat. How about this? What if you have a circle? X squared plus y squared equals to r squared, right? And you want to find the area, say, of this piece. So that's y is equal to the square root of r squared minus x squared, right? And if you integrate, say, from minus r to r, that should be the area. Right? But by symmetry, that's also twice the integral from 0 to r of the square root of r squared minus x squared, right? But then I can say that is actually what? It is 2. So the 2's cancel, right? So I get r squared inverse sine of x over r evaluated from 0 to r. You're like, what? But, hey, but what? See this? These guys right here. What happens when you put x equal to 0? What happens when you put x equals to r? 0. So when we evaluate that part of the antiderivative at the bounds, 0. The only thing that survives is the inverse sine of what? Inverse sine of r over r, otherwise known as 1. So we get pi r squared over 2, which makes sense. That's half the area of that circle. So this is something you couldn't do last semester. But maybe you were asked to calculate the area of that on a test, right? But that was the trick question. Basically, the point was, oh, it's a circle, so I know the area is pi r squared, right? But now we can derive it from more basic principles, like so. Thanks, guys. See you tomorrow.